We'll be looking at similar polygons. Of course, with congruent polygons, we had to have the same shape and same size. With similar, it's just the same shape. Now, at first glance, you might think that these are dogs. They're actually cows. They're disguised as poodles. All right, those are actually cows. They are similar to each other. Why are they similar? Take a look at them. The larger cow is exactly twice as tall as the smaller cow. The larger cow is exactly twice as long as the smaller cow. Right? If you look at the height, the vertical units, one of them is 8 tall, the other is 4 tall. If you look at the length, the horizontal units, one of them is 6, and one of them is 3. So those are proportional. They're similar to each other. And of course, when we talk about a ratio, it's a fancy way of saying it's a fraction. And if we set two fractions equal to each other, we say that the ratios form a proportion. One way I can check is, all right, let's reduce each fraction. Of course, if I factor, 8 is 4 times 2, 12 is 4 times 3. I cancel the common factor, leaves me with 2/3. Same method for 6/9. The largest common factor that goes into both 6 and 9 is 3. So the 3's will cancel. Leaves me 2/3. Since both fractions reduce to 2/3, I can say that the ratios are equal to each other, and therefore the ratios form a proportion. We can also cross multiply. Twelve times 6 is 72. 8 times 9 is 72. Now, you don't have to start with the 12 times 6 is 72. I could have started instead with the 8 times 9 is 72. The key is making sure that when we use the cross products, I'm using the numerator from one fraction with the denominator from the other fraction. So those are two different ways of confirming whether or not two ratios form a proportion. Now, physical abuse of a calculator would be when you take your hammer and you smash the calculator with a hammer. That is one thing we just do not want to do. Then, of course, there's the mental abuse of a calculator. You should notice that previously, when I reduced 8/12 to 2/3, or when I did 12 times 6 is 72, I did not grab a calculator for any of that work. Right? That type of work needs to be done by hand, not by a calculator. Let's try a couple. Do these ratios form a proportion? Okay, now the directions say let's reduce to lowest terms. So if I start with 24 over 30, It looks like their common factor is 6. I should say the greatest common factor is 6. Of course, the 6's cancel, leave me 4/5. How about 28 over 32? Well, greatest common factor is 4. The 4's cancel. 7 over 8. That does not match 4 over 5. No, the ratios do not form a proportion. How about this pair? 18 over 24, 15 over 20. Well, with 18 over 24, the greatest common factor is going to be 6. So I can rewrite 18 as 6 times 3. I'll rewrite 24 as 6 times 4. So that will reduce to 3/4. 15 over 20, greatest common factor is going to be 5. 5 times 3 for my numerator, 5 times 4 for my denominator. Both ratios reduce to 3/4. So yes, they form a proportion. Now, I don't expect you to understand everything you're about to see here. We want to jump in a time machine and take a look at why I'm insisting that we try reduce fractions by hand. If you encounter a fraction like this, how on earth would I reduce it? Well, I can only cancel factors, which means I'd have to first factor the numerator and denominator, and then identify the common factor and cancel that out. And that would leave me with x minus 5 over x minus 7. Now again, I don't expect you to follow along with all that right now, although we've done bits and pieces of that. But the reason why we don't want to just grab a calculator to reduce a fraction, we need to understand the method of reducing the fraction by hand. We need to get in the habit of factoring, canceling the common factor. Trust me, you'll appreciate it next year. Okay, back to geometry. Can we solve a proportion? Right? Reducing the fractions won't work here because I don't know how to reduce x over 25. So instead of reducing the fractions, we got to go back to our cross multiplication. On one side of the equation, I need 15 times x. On the other side, I need 6 times 25. Does not matter which one you do first. Of course, 6 times 25 is 150. I don't want 15x. I better divide by 15. X would have to be 10. I usually like to have my variable on the left-hand side of the equation, and so that's why I did 15 times x first. But if I'd wanted to, I could have started with 6 times 25 and put that on the left-hand side, and then 15x would have been on the right-hand side. I still would have gotten an answer of 10. Ooh, looks like there's room for another example. Hey! The x is in the denominator instead of the numerator, and it looks like there's a minus 7 with the x. This looks a little bit more interesting. So on one side, I need to do 15 times 4. On the other side, 10 times the quantity, x minus 7. Well, 15 times 4 is 60. And then using the distributive property, 10 times x was 10x. 10 times 7 was 70. Of course, there's a subtraction symbol between the x and the 7, so I need the subtraction symbol between the 10x and the 70. Well, is there any adding or subtracting I can undo? Yep, I'll add 70 to each side, because addition is the opposite of subtraction. Now I'm going to ask myself, is there any multiplying or dividing I can undo? Yeah, look, 10 is multiplied by x. Opposite of multiplication is division. Divide both sides by 10. X is 13. Wow, still a lot of room here. Carve out a space for one more example. Ooh, there's more than one x. This is going to be fun. On one side, I've got to do 12 times the quantity 4x minus 2. On the other side of the equation, I need 27 times the quantity x plus 3. Again, it doesn't matter which one is on which side of the equation, as long as the 12 multiplies the 4x minus 2, and as long as the 27 multiplies the x plus 3. Well, it looks like we need to use the distributive property on each one. 4 times 12 is 48. 2 times 12 is 24. Keep track of your x, keep track of the subtraction symbol. 27 times x is 27x. 27 times 3 is 81. Now, to isolate the variable, I want all my variables on one side. So perhaps here, since I like my variable usually on the left-hand side, I'll subtract 27x. Whoops, hit too many bumps there. Subtract 27x from each side. And then, of course, I don't want the minus 24 there. So I'll add 24 to each side. $21x is 105. Wait, I don't want 21 of those x's. So, of course, we will divide by 21. Remember, anytime if you think I'm going through an example too fast, you can pause the video, you can stop the video, you can rewind the video. Okay, so now we can reduce fractions, we can solve proportions. Let's get back to geometry and see how we can apply these skills to geometry. Now again, similar means they're the same shape, but not necessarily the same size. Notice the first triangle has side lengths of A, B, and C. To be similar, I'd have to multiply each side by the same transformation factor. I'd have to multiply each one by the same number. In this case, the number is k. Notice we don't use the equal sign. We don't use the congruent sign. Instead, for similar, it's just kind of like that tilde symbol. Now remember, we did this earlier in the school year when we were plotting the points, and then we decided, hey, let's multiply everything by 2 and plot the new points, or hey, let's multiply everything by 3 and plot the new points, and we'd make an object larger or smaller. That's what's happening here. And just like before, the angles are preserved. The size may get larger or smaller, but it stays the same shape. It keeps the angles. Of course, if the angles are congruent, that means their measurements are equal. So if I talk about the shape, we'll say congruent. If I actually talk about the numbers involved, we'll say equal. And they like to call their scale factor K. Different math sources will use different letters. K is pretty common, however. Now, key thing here is make sure that you match up corresponding sides. You can't mix and match. Of course, the corresponding angles are congruent. And for any pair of corresponding sides, if I reduce the fraction, I should get the same value for K. That's the scale factor. Okay, are these two triangles similar? They sure look like it, but just looking and kind of guessing and eyeballing is not going to work out. So I got to make sure that I compare XY with RS, because those are corresponding sides. And it looks like 12 over 20. I reduce the fraction, get 3/5. Now I'll compare YZ to ST, because those are corresponding sides. So 18 compares to 30. I get 3/5. Notice if I put XY as the numerator in the first ratio, I better put YZ as the numerator in the second ratio. Right? On each ratio, I'm putting the smaller triangle as the top, the larger triangle as the bottom. It doesn't matter which one I decide to put on top, as long as I'm consistent. So ZX has to be my numerator. So 15 has to be my numerator. Of course, that corresponds to TR, which is the 25. Yeah, they're proportional. Because every pair of sides reduce to the same scale factor. So in this case, we say K is 3/5. Before you do the IXL today, I'm going to have to give you a slight warning about the order. Right? To me, it doesn't matter, but for IXL, it gets kind of grumpy if you don't do it in order they expect. Okay, well in this case, we don't have to show they're similar. We're already told the triangles are similar. We just want to find that value of X. Of course, corresponding side lengths are proportional. So I've got to write a proportion. Of course, somewhere in this proportion, I better have the side EF. Because that's what I'm trying to find. Now, I stole this off the internet, and they decided to start with NM, which is fine. You can start with any side you want. But since I took that side from one of the triangles, I must take the corresponding side from the other triangle now. Right, why they chose to start with MN, I don't know, but it certainly corresponds with DE. Now, the top of the next fraction has to come from triangle MNP. And of course, they have to choose side NP because you know we're trying to find X. So they had to pick NP because NP corresponds with EF. Right, so the first fraction has corresponding parts from each triangle. Second fraction, corresponding parts from each triangle. Doesn't matter what triangle I start with, but once I make that choice, I must be consistent. So if I decide that triangle MNP is going to go on top, it has to go on top of every single fraction. And then, of course, the corresponding part of the other triangle has to go on the bottom of each fraction. Of course, we can now substitute the values. MN, of course, was 18. DE was 15. NP was 30. EF was X. Cross multiply. 18 times X has to be on one side of the equation. 15 times 30 is where that 450 came from. Again, I just stole this example off the internet, so they didn't show all the step-by-step work there. But the cross products is where that came from. And of course, solving for X, better divide both sides by 18. So you get 25. I was lazy and didn't want to do all the triple work myself. Quadrilateral bird, quadrilateral cats. Something tells me this one's not stolen off the internet. Here's one I did myself. Ooh, we're not looking for the value of X. We actually want the length of segment IR and the length of segment AT. Well, gotta set up a proportion. Since IR is one of the lengths I want, I'm going to start with IR. Now, IR corresponds to AT, right? I was the second letter in bird. A is the second letter in cats. R is the third letter in bird. T is the third letter in cats. Now I better pick a pair where I can get just pure numbers. So BD is 8. BD compares to SC, which is 6. So I try to wisely pick a pair of sides that corresponded that would not have the letter X involved. Right? B starts bird and D ends bird. C starts cats. S ends cats. So if I'm going to grab BD, I got to grab the C and the S. In this case, I put it as SC just because of the way it looks on the paper there. Right? Or the letters doesn't matter. I can call it SC or CS. But if I grab the B and the D, I have to grab the C and the S because I have to have the corresponding letters. So I've got a 3x plus 1 is IR. 2x plus 2 is AT. Eight is our BD. 6 is our SC. Of course, I didn't have to pick that pair. I could have picked a DR and ST as my other pair, and I would have a 12 and a 9. I just decided to use the one with the 8 and the 6. Probably because those are the smallest numbers available. Cross multiply. Six times the quantity, 3x plus 1. 8 times the quantity, 2x plus 2. Use the distributive property. Isolate the variable, so I'm going to subtract 16x from each side. 18x subtract 16x is where that 2x came from. Now I'll subtract 6 from each side. 16 subtract 6 is 10. Now I'll divide by 2. 10 divided by 2 is where the 5 came from. So x is equal to 5. Now, before I start celebrating, I've got to look back and say, ooh, I'm not looking for X. I want the length of segment IR and the length of segment AT. Of course, IR equals 3x plus 1. Substitute the value for X, get an answer. AT, of course, is 2x plus 2. Substitute the value of X, calculate, get an answer. Now, before we ride off into the sunset, a word of caution about the IXL. Otherwise, you'll get very frustrated. The program is super picky about the order. So here's a screenshot of one of the actual questions on the IXL. And if they ask for the similarity ratio, whichever polygon they list first, that has to become your numerator. So my VW is on top of the fraction because that polygon was listed first. The FG is on the bottom of my fraction because that polygon was listed second. So I've got 9 divided by 3 comes out as 3. The answers today might just be a plain old number like 3, or you might end up with a fraction like 2/7 or 5/4. Right? First polygon has to go on top. Second polygon has to go on the bottom. Otherwise, you're going to get a lot of incorrect answers and you'll get frustrated. Okay, let's ride off into the sunset. You've got a worksheet that you should do first. Kind of check answers as you're going along. And then the IXL is P1, the similarity ratios. And there's a gorgeous sunset to ride off into.